Conservative force fields belong to the topic of work and power in classical mechanics. But what exactly is a conservative force? First, we define a force field. Casually speaking, this is just a force whose orientation and strength depends on where it acts. Mathematically, the force is a function of space. This can be the Cartesian coordinates, spherical coordinates, whatever you want. Remember that forces are vectors, so this means that every component of the force is dependent on where it acts. Look at the gravitational force of the Earth. If we just look at two components, then we can see that the x and y components act differently depending on where we look at them. The next thing we need to understand conservative force fields is the concept of work. Work is defined as the integral over the force along a certain way. Mathematically, this is the integral of the force in a dot product with a vector of dx, dy, and dz. And physically, work is a measure of how difficult it is to move something from A to B. For instance, for a frictionless surface, it requires no effort to slide a mass left and right, but it does require some energy to lift it up, thus working against gravity. This example can help us understand the concept of a conservative force field. A force field is conservative if the work between 2 points A and B does not depend on the path how we get from A to B. So if this is A and here is B, then we can go via two paths. First right, then up, or second up, then right. If the force field is conservative, this does not matter. We would get the same result. In other words, the difference between the work along path 1 and the work along path 2 should be 0, since they are the same. Now, by exchanging the starting and end points, we can switch the sign in front of the integral. Next, we can write these two integrals together into one by using the notation for a line integral. So a convenient definition of a conservative force field is that if we move in a closed loop along a path C, then the work is 0. The circle on the integral means that we move along a closed line, and the C under the integral sign says that we consider a curve C, which in this case takes us along path 1 from A to B, and then along path 2 back from B to A. There are actually two more definitions of a conservative force field. So we have our first condition that the work inside such a conservative force field is 0 if we start and end on the same position. Second, we can define a conservative force field by saying that the curl of the force field is 0. Remember, the curl of a vector is a cross product of this vector of derivatives with the vector. And third, another condition is that if we can calculate a function phi such that when we take the negative divergence of this function, we get the force back, this force is conservative. And by the way, this function is then called the potential for the force. Now you might be wondering if one definition is better than the other. However, for our purposes, they are in fact equivalent to each other, which means there is no best definition. We can use Stokes' theorem to write the closed line integral over the force F as a two-dimensional integral over the area enclosed by the line C of the curl of F. If we use the second definition, then this expression is 0, just like the first definition wants. Now for the third one, let's assume there is such a potential phi. If we take the curl of this expression, we can use an identity of vector calculus that the curl of a gradient is 0. This means definition 3 is as good as definition 2, which is in turn as good as definition 1. And that's pretty much it for this time. Thanks for watching.